Hi, Tom the Professor here. It's time for another problem. Let's get started. It took me a little while to decide how to best frame this problem. When we were younger, we used to spend a lot of our time on the playgrounds playing on the merry-go-rounds. They were the kind that you had to push by yourself. We would take it upon ourselves some days to see just how fast we could push it. We would get our best pushers on the outside, and then maybe one or two people riding the merry-go-round hanging on as tight as they possibly could. And then we would push it faster and faster and faster and faster until someone would fly off. Now, nobody really ever got hurt doing this, but that's probably why they don't have merry-go-rounds on many playgrounds anymore. Way back in history, we humans first looked up to the skies and tried to describe how things moved. The simplest solution was that the Earth was stationary and everything moved around it, including the sun. We've learned since then that that's not the case. The sun is actually the center of our solar system, and the Earth rotates around, causing day and night. One of the main objections to this idea, though, way back in the day, was that the Earth would be spinning so quickly that people would simply fly off into space, much like what happened with us on the playground and the merry-go-round. With this problem, we'll be able to show that that's not exactly the case. Once again, the text will be on the screen, although it's pretty short this time. And we will start out with, what do we know? We'll take the mass of a person to be 97 kilograms. That's about average. And we're going to round off the radius of the Earth to be an even 6,400 kilometers. We're going to use that value in meters, so be ready for it. Other things we need to know. If a person standing on the surface is going to stay on the surface of the Earth as it rotates, that person is going to have to travel in a circular motion. Now, what is required to travel in a circular motion? There must be a centripetal force acting on that particular person. If that person doesn't have a sufficient centripetal force, then yes, they will go flying off into space. So what we want to find in this problem is what centripetal force is required for a person to stay on the surface, and is there a force, maybe gravity, that is large enough to provide such a centripetal force? So what do we need to know in order to calculate the centripetal force? Well, centripetal force depends on how fast you're going around the circle and the radius of that circle, along with a few other factors. The actual equation is you take the mass, the centripetal force will be the mass of the object, this our person, times the ratio of the speed squared divided by the radius. Now the mass is given to us, 97 kilograms. The radius is going to be the radius of the Earth since we're standing right at the surface. But what is that speed going to be? We'll have to find a way to calculate the speed. So let's see. In order to calculate speed, let's take and use our average speed equation. Speed is distance by time. Okay, but what's the distance we're going to be traveling? To travel once around a circle, we use the circumference formula. So the distance will be 2 times pi times the radius of the circle. We have all of those values, so let's plug those in. We have 2 times pi times, here we have 6,400,000 meters. That's converting from kilometers to meters. And when we do that, we get a value of 40,267,520 meters, the distance around the Earth at the equator. Rounded off, of course. The other thing we will need to figure out the speed at which someone is traveling at the equator is how long it takes to travel that distance that we just calculated. Well, that's pretty easy. The Earth rotates once per day. It's kind of convenient that we chose that, isn't it? It's slightly less convenient that we split that day into 24 hours, and each of those hours into 60 minutes, so that gives us 1,440 minutes per day. And then 60 seconds per minute, which gives us 86,400 seconds per day. Now I'm using seconds here because I want a value for our speed in meters per second, so that when we calculate force, we have the unit of Newton that pops out. So we'll plug in the 40,267,520 meters, and we will divide by 86,400 seconds to get a speed at the equator of 466 meters per second. Now that is a straight line speed, so if the centripetal force is not big enough, we're traveling off into space at 466 meters per second. All right, so back to our centripetal force equation. Now we have all the values we need, so we'll plug in the 97 kilograms. We'll plug in the 466 meters per second. We'll square that and divide by the 6,400,000 meters for the radius of the Earth. And that gives us a value for the centripetal force needed to travel in a circular path at the radius of the Earth to be 3.3 newtons. Now, 3.3 newtons is not a huge value. But is gravity going to be large enough to cover that 3.3 newtons? Well, let's use the simple formula to calculate the weight of an object. We'll use the mass times the acceleration due to gravity. If you want to, you can go back and use universal gravitation with the mass of the Earth, which you'll have to look up because it's not given in this particular problem. You can use the same radius of the Earth for the distance between the Earth and the person, and then use the mass of the person, the universal gravitational constant, and calculate that. But you're going to get a value very close to what we'll get here using this equation here. So throw in 97 kilograms, 9.8 meters per second each second for the acceleration due to gravity, and that gives us a value of 950 newtons. The Earth is pulling on us with a value of 950 newtons, and all that is required in order for the Earth to be spinning at 466 meters per second is 3.3 newtons. So, no, we won't go flying off into space because the Earth is rotating at 466 meters per second in order to produce the day-night cycle. If you like the video, make sure you like and subscribe. If you have any questions, hit me up on social media at the handle on the screen. Check out the blog, tomteacheспhysics.com. And, of course, pick up some merch to help support the channel and everything I do. Until next time, I'll see you next time.